Okay, guys, let's go ahead and get started. So today we're still reviewing necessary material. Focus my camera. Okay, so today we're still reviewing necessary material in order to get into the main topic of real analysis. In particular, we're going to be looking at section 1.2, which is on mathematical analysis. Or not mathematical analysis, I'm not talking about mathematical induction. Okay. Okay, so well, what is mathematical induction? So mathematical induction is a proof technique that can be used to establish the validity of statements in terms of the natural numbers. Okay, so this is a brief description of what this is. So in particular, it's a proof technique, okay? And it's a proof technique that's used to determine whether or not statements that are given in terms of the naturals are true for all natural numbers. Before formally defining what mathematical induction is, we need to recall a fundamental property of the natural numbers first. So this property is called the well-ordering property. Well-ordering property of the naturals. Okay. Now, sometimes people will refer to this as WOP. Yes, a nod to Cardi B. So, okay, what does this say? So, every non-empty subset of the naturals has a least element. Okay. So this is a fundamental property of the natural numbers that will be used in establishing mathematical induction. Another way of thinking about this, so this is like equivalent to saying something like, so if S is a non-empty subset of the naturals, okay, then there exists an element M of S such that M is less than or equal to K for all K in S. Okay. So this should make sense, right? Like you have some non-empty subset of naturals, it's just a bunch of numbers, right? And there's going to be a smallest one in that set. In this case, we call that M. Okay. So now that we've recalled this this well-ordering property, we can write down the first principle of mathematical induction. Okay. By the way, I'm really excited. Tomorrow I'm getting another one of these. So next lecture, it's going to be a lot wider. I won't have to like erase over and over again. Okay. So here it is. So this is the principle of mathematical induction. And I'll call this version 1, because there is going to be another version. Okay. So we're going to say, let S be a subset of the natural numbers. With the following properties. Okay, so 1. Okay, maybe. So property 1. 1 is an element of S. And property 2. For every K in S, K plus 1 is also in S. So if this is the case, then S is equal to the natural numbers. Okay, so let's take a moment to think about this. And you can speak up, by the way, all of you. Does this make sense? So if S is some subset of the naturals, and if both of these properties hold, then S must equal the set of naturals, right? Like if 1 is in there, and if K is in there, then K plus 1 is in there. Does it make sense that this holds? And get some yeses, some nos.
Yeah.
Yes.
Yeah, that makes sense.
Do you think it needs proof?
I think you're gonna make us prove it.
This is true, but I'll prove it for you, so it won't be so bad, right?
We just need to prove it for one which exists in S, right? And then do it from there.
Well, you're probably jumping ahead to actually using this to prove statements. This is just a statement about the structure of this set S, which will imply, if you've encountered induction before, which will imply this other technique that we're going to call mathematical induction. But I like that you're familiar with the notion, so that's good. But yeah, so let's prove it, and it's actually not so bad. The only bad part is that I'm probably going to run out of space. So we're going to do this by way of contradiction. So I'm going to say by way of contradiction. Suppose S does not equal the natural numbers. So by the way, we're assuming that S is a subset of the naturals. And we're assuming that in this case, it's a strict subset of the naturals. So maybe I'll just say it is a strict subset of the naturals. It's not equal to the naturals, right? Okay, so if it's a strict subset of the naturals, then so maybe not then, you can say, so by way of contradiction, suppose it's a strict subset of naturals, and let maybe like Q equal to the naturals set difference X. Okay. So maybe now we can say since S is a strict subset of the naturals, observe that Q is non-empty. Does that make sense? Up to this line right here? Right, so if it's strictly contained in there, right, there's elements in the naturals that are not in S, right? So if we look at Q as the naturals minus S, there's still stuff left over, which means that Q is not empty. How about that? Where are y'all at?
Yeah, that makes sense.
Okay. And again, this just implies there's things in there that are not in there. And since Q is the difference, it's going to have stuff left over. So Q is going to be not empty. Okay.
Q is just like an arbitrary letter you picked, right? It doesn't mean irrational.
Yeah. Actually, let me. So I was literally right before you said that, I was thinking that in my head. So maybe like, I don't know. What's one that's not E? E. I guess. Look at E. Okay. So then notice that E is a non-empty subset. So moreover, maybe. Since E is a non-empty subset of N, E has a least element, say M. So M is the least element of the set E. Okay, and again, this is by well-ordering principle. Well, okay. So every non-empty subset of naturals has a least element. We know that E is non-empty and a subset of naturals, so it has a least element. We call it M. So, okay. So then M minus 1, which is strictly less than M, is a natural number. So it says number, by the way, if you can't read it. It's a natural number, not in E. Okay. Okay. And then we should note, since maybe that note. So if n was equal to 1, then n minus 1 is 0. That wouldn't be a natural number. So this is a natural number. N minus 1 is a natural number, not an e. The fact that this is a natural number is because, so since 1 is an element of S by assumption 1. Right, so we're assuming that 1 is in that set S, and if 1 is in S, then it's definitely not in E, so we know that M is not equal to 1, so that means that M minus 1 is a natural number. It's not, it's greater than 0, some number greater than 0. Okay? Okay? So, since M minus 1 is a natural number, and it's not in E, we can say hence M minus 1 must be in S, right? So S and E together make up the natural numbers. Since this is a natural number, it's strictly less than the smallest number in E, it must be the case then it's in S. Okay? Okay, so we just concluded that, what does all this say? That if M is the least element in E, then M minus 1 must be in S. Right? And M minus 1 is not in E. So N minus 1 is not in E, and it is in S. That's what we concluded. So furthermore, however, property 2, if something is in S, then if you add 1 to that, it's also S. So property 2 implies M minus 1 plus 1 equals to M is in S. Why is that bad? But what does this say? It says if you have something in S and you add 1 to it, it's also in S. We're assuming that these two things hold for that set S. We know that that's in there, so if we add 1 to it, that is also in there. But why is that bad? What does that do? Why? Not bad, but like we're doing a proof by contradiction, right?
Because then the ones cancel each other out and it's just M equals M.
Well, not quite. Let me see. This is all I'm saying is that we know that this is in the set S, and if we add 1 to it, by this, we're assuming that this holds for the set S. That must also be in there.
M is on E, but we said earlier that E is the set that is not in S. So that contradicts itself.
Right. So, yeah, it's just a contradiction. So a contradiction since M is the least element of E, right? And E doesn't contain anything from S, right? So M is the least element of E, which means that M minus 1 must be in S, but by property 2, M minus 1 plus 1 is in S, so we get these two things together. That's a contradiction because these sets are disjoint from each other. Since that, which is the same thing as saying A is not in S. Okay, so that's the contradiction. If we assume by contradiction that S is not equal to the natural numbers, which means it's a proper subset of the naturals, then E, which is the set of all naturals that don't belong to S, is non-empty, and it has a least element, M, by the well-ordering property. Okay? Now, M can't be equal to 1, right? So M cannot be equal to the element 1, because under this assumption here, 1 belongs to S. So that can't be equal to 1. So we know that M minus 1 is a natural number. Is it a natural number because M is greater than 1? And since M was the least element in E, this is not in E, which means it must be in S. But property 2 says that if anything is in S and if you add 1 to it, it's also in S. So since M minus 1 is in S, M minus 1 plus 1 is in S. But that's the same thing as saying that M is in S. And that's the contradiction because M belongs to E, which means it's not in S. And so that completes the proof of the principle of mathematical induction. Okay. Okay, but so this is phrased in terms of sets, right? But when we typically use mathematical induction, we phrase it in terms of propositional functions that whose truth value relies on some subset of the natural numbers. So we replace these element-wise arguments with proposition truth, right? And we'll see what that means when I write down the second version of the principle of mathematical induction right now. Okay. So now this would be version 2, which differs slightly from the version that's given in the textbook. This is the way that I like to write it. Okay, so let n not be a natural number, and let P of n be a statement for each natural number n greater than or equal to n not. Okay. If the following two statements hold, so P in not is true, and for all k greater than or equal to n naught, pk implies pk plus 1 is true. So if these two things hold, then Pn is true for all integers n greater than or equal to n naught. Okay, so this is the statement of the principle of mathematical induction that we will use most often in our proofs. In our proofs that require induction. Okay. Not all proofs will, but when you have a statement that's claiming something to be true for a subset of the natural numbers, then oftentimes you can use this technique. So here, this property 1 here is often called the base case. That's property 1. And then property 2, here, this is called the inductive step. So all of this part 2. Okay. Now, so in order to prove a statement by mathematical induction, you first verify the base case, and then you prove the inductive step. These two statements together will prove the statement Pn true for all values greater than or equal to the first integer that you picked, or first natural that you picked to satisfy your base case. Okay, so I guess the best way to illustrate this is with examples. So for the rest of the class, we're just going to walk through various inductive proofs. And so make sure that you have this written down or have the textbook pulled up. Put this in front of you because we're going to use it. Okay. Okay, so we're going to start with probably the first inductive proof that everyone that's learning induction does. So here's my claim. So for each natural number n, if you sum the first n natural numbers, then this is equal to 1/2 of n times n plus 1. Okay. So it's a closed formula for whenever you're summing the first n natural numbers. We're going to prove this using induction. Okay. So there's many different ways to do this. Because of how small my board is, I might not write it out all the way, but I'll try to fit it in the best I can. So, so maybe start by saying let P of n be the statement 1 plus plus n is equal to 1/2 of n times n plus 1. Okay. And then say we will prove the claim by induction on n. Now, this first sentence here, you wouldn't necessarily need to include. I just want to include it so that you see how it relates back to the principle of mathematical induction that I just erased. You could get away when writing this proof by just saying, we will prove the claim by induction on n. Okay. So then you can break up the proof into several pieces and say something like the base case. Observe. P of 1 is true, i.e. 1 is equal to 1/2 of 1 times 1 plus 1. So if you consider the statement P of 1, it's 1 is equal to 1/2 of 1 times 1 plus 1. This is just 2, so 1/2 of 2 is 1. So this satisfies our base case. So next we want to look at the inductive step. So now we want to show that P of k implies P of k plus 1. So we have to assume something. We have to assume, so, okay, let's say we want to show if P of k, then P of k plus 1. And so this is the inductive step. So in order to do this, we assume P of k is true, and then we show that P of k plus 1 is true. Okay. So in order to do this, we have to assume P of k. Right? We're trying to prove if that, then that. So we're going to assume the hypothesis, which will be called our inductive hypothesis. So that right there is our inductive hypothesis. So we're going to say, for our inductive hypothesis, suppose P of k is true, i.e. that 1 plus dot up to k is equal to 1/2 of k times k plus 1. Suppose the sum to k is equal to 1/2 k times k plus 1. Okay, and we want to, under this assumption, show that P of k plus 1 is true, right? So this is this right here. I'm going to underline it for you. This right here. That assumption is assuming this. And that's called our inductive hypothesis. And we want to show that this assumption implies that. So again, if I put it down in red, it wouldn't go down with the formal proof. I'm just using the red to highlight what's going on in the background. So this is what we want to show. We want to show this to be true. We've assumed that, and now we want to show that. Okay, so next we're going to consider the sum up to k plus 1 integers, or the natural number. So next, observe. Okay. Next, observe that if we look at the sum up to k plus 1, by inductive hypothesis, we know that there's an equation for that sum. It's precisely that, right? So we can replace that by that equation. And And then we have this left over. Right? So we want this to look like something. Okay? So what does this look like? And again, this isn't a part of the formal proof, but what does P of K plus 1 look like? It looks like this. Dot, dot, K plus 1. If that's equal to 1/2 of K plus 1 times K plus 1 plus 1. This is a 1 right here, if you can't see it. The sum up to K plus 1 is equal to 1/2 of K plus 1 times K plus 1 plus 1. It's like everywhere you see an N, you put a K plus 1. And that's what we want to show using our hypothesis to do the same. All right, so can we get that to look like that? Okay. Well, I see that there's a common factor of K plus 1 here. So maybe I can factor that out. Maybe it's K. Or maybe if I can combine like terms first. So this would be K times K plus 1 plus 2 times K plus 1 over 2. Now factor out the K plus 1. And then on the inside, we're going to have K plus 2, right? Once you factor out the K plus 1, which is like saying K plus 1 plus 1, and then there's the denominator 2. So what did we see? That if we sum 1 to K plus 1, we get that 2 belongs up right there, right? And that's, but we sum from 1 to K plus 1, we get what we wanted. This statement here, this is equal to that. This, all of this shows that P of K plus 1 is true. So then we just finish it off by the principle of mathematical induction, you're done. We are done. And again, why? Well, we satisfied the base case. So the statement is true when n is equal to 1. And then if we assume the statement is true for k, then the statement must be true for k plus 1. That's what we've shown. We assumed it's true for k right here. And then under that assumption, if we look at the sum of the k plus 1, using that inductive hypothesis, we can reduce this to that, which is equivalent to the desired formula for the P of k plus 1. So we've satisfied conditions 1 and 2 of the principle of mathematical induction, which means that we've proven the statement for all n greater than or equal to 1. And we're done. Okay. So maybe let's look at a different type of example. All right, so So what's my claim? Yeah. So if A and B are real numbers, then A minus B is a factor of A to the power n minus B to the power n for all natural numbers n. Okay, and we can prove this by induction. So let's go ahead and look at the proof. So I'm going to change up the style a little bit. So I'm going to get rid of the PN notation. I'm just going to say we will prove the claim by induction on N. Okay. So for our base case, we're going to observe that A minus B is a factor of A to the power 1 minus B to the power 1. This is a 1, by the way, you can't see it. I'll try to make it bigger. 1. 1. Right. They're equal, so it's surely a factor. All right, so this satisfies our base case. So now we need our inductive step. Inductive step. Okay, so now we need to assume that this is true for K and then show that that implies that it's also true for K plus 1. So for our inductive hypothesis, we're going to assume that it's true for K. We assume A minus B is a factor of A to the power K minus B to the power K. Okay. Next, observe that A to the power K minus B to the power K. So actually plus 1, sorry. A to the power K plus 1 minus B to the power K plus 1. Okay. Our goal now is to show that A minus B is a factor of this. Keep that in mind. So there's a little trick that we're going to do. We're going to add 0, but a fancy version of 0. Minus A to the power, let's say, I need to write it out first. Like, notice if that's true, right? That and that is just 0, so it's like I added 0 to both sides of the equation. Now my goal, right, is to show that this has a factor of a minus b, right? Now, in doing so, we're going to have to make use of our inductive hypothesis. And our inductive hypothesis has a to the power k minus b to the power k. Now, if what about this? I see k plus 1 with a, and I see 1a right there. So what about if I do b to the power k, like that? So now this is still 0, right? But now here, if I factor out a from here and there, I get a times a, I'll just write it out. I factor out an a from here, I get that times a to the power k minus b to the power k. Right? And over here, can I factor out anything? Well, I can factor out a b to the power k. And I'm left with a minus b. Does that make sense? All I did was add 0 in such a way that I could use the inductive hypothesis. And I see that, oh, this has a factor of a minus b is a factor of that. And then here, a minus b is clearly a factor of that. So a minus b is a factor of both of these pieces. Okay. So by our inductive hypothesis, a minus b is a factor of a times ak minus bk, right? Because it's a factor of that. Okay. And maybe like moreover, a minus b is clearly a factor of this thing, right? bk times a minus b, right? Because it appears right there. You know, I'll go ahead and I'll label this equation here. I'll label that 1. Okay, so you can label equations to reference them. So you can say, since a minus b is a factor of both terms from 1, a minus b, I guess I'll just finish it right here, is a factor of ak plus 1 minus bk plus 1. And then that finishes off the proof. And so a minus b is a factor of this because it's a factor of that by our inductive hypothesis. A minus b is a factor of this term since it just appears there. So since a minus b is a factor of both these terms, it's a factor of the whole thing, which means it's a factor of this, which proves the statement by induction. Okay. So for those of you who haven't seen induction before, you're probably gonna have to brush up a little bit and read section 1.2. So I guess I'll just give the suggested homework now. I'm not going to erase it all, just in case some of you are still writing them there. So this is the suggested homework. So read section 1.2. And then let me see if I can find any good problems to do. So then, and then from this section, problems. One, two, maybe 6. $13 and $14. Okay. Okay. Any questions?
When is this due?
It's not due. These are just suggested. All problems that will be due, I will put on Blackboard.
Oh, okay.
But we're not there yet. I just want you to get some practice in. And then next class, ask them related problems if you have trouble with them.
Okay, so it's the same as last time when you you just wanted to you want us to do it for ourselves basically, right?
Right, right.
Oh, okay.
Okay. Any other questions? All right, well, I guess that's it. Thank you for joining me. And then next time, we will go to section 1.3 and I'll try to have some more feedback from you as I'm lecturing. Okay, I'll prompt you with a lot more questions next time. All right, y'all stay safe. And I will see you on Thursday.
Have a good afternoon, Professor.
Thank you.